Our eyes can detect a ball that is moving towards us in a matter of milliseconds and prompt us to either catch it or take evasive action. An eventing system is analogous to this. Events in a business setting could range from something simple, like a customer clicking on a particular button on a website, or more complex, like a delivery truck entering a supply depot. But regardless of the complexity, just like our eyes, a good eventing system needs to be fast, accurate, and prompt an immediate and appropriate response to the unfolding event. From a database perspective, an eventing system requires a few capabilities. The first is functional coverage. In the case of the truck entering a supply depot, the database has to use a geospatial intersection function to analyze the GPS signals coming from the truck to determine if it has entered a specific area. This requires in-database functions that can analyze your data in place to tell you if an event has occurred. The second capability is speed at scale. Eventing systems usually deal with a large amount of streaming data from sensors and IoT devices, and events typically require an immediate response. So, all in database functions and computations need to be performant at scale to prevent any lags in your eventing system. The third capability is the ability to cascade or chain computations. The signal for an event is typically carried through a data stream. An always on eventing system has to continuously listen for signals and automatically trigger a change that cascades down a series of computations until the final response, without any additional human input. At a high level, we can classify events into two groups: those that happen in the digital realm, for instance, a button click on a website, and those in the physical or spatial realm, like the truck entering a supply depot. Generally speaking, digital events are much easier to discern since they can be captured using event listeners within the application itself. Physical events, on the other hand, are much harder to discern because they require us to process streaming data from sensors and IoT devices to infer a signal from them. This video shows how to use Kinetica to set up eventing pipelines for the latter, more complex spatio-temporal event type. More specifically, we will look at events related to tracks, that is, the path that an object takes over time. Kinetica has a wide range of capabilities, but it really stands out because of its in-database suite of spatial and temporal functions. In this demo, we play the role of an analyst that works for the US Coast Guard, and we will use Kinetica's in-database spatial and temporal functions to set up an eventing system that observes ships in the Gulf of Mexico region to identify three types of events. The first is when a ship enters or passes through a specific area. The second is when ships dwell or loiter in and around a particular location. And the third is when a ship gets within a 2-meter distance from another vessel. Let's jump in. Let's log in. This is Workbench, which is the user interface for Kinetica. Let's open up the workbook for this demo. We'll be using some shipping data from the Gulf of Mexico region for this demo. This data is being streamed in via a Kafka topic. Each message in the Kafka topic contains the lat and long coordinates of a particular ship at a given point in time, along with some metadata. Each ship in the data is identified by a unique ID variable. Let's load this data into Kinetica. Here I'm setting up the credentials for the Kafka cluster and using that to create the data source for the Kafka topic. Next, we create the table in Kinetica that will receive all the messages from the Kafka topic. The schema for this table matches the Kinetica topic. The next query loads the data into this table from the data source we just created. The map below is set to update every few seconds, so we can see the tracks appear on the map as the data is ingested into Kinetica. We can also check out the ship_tracks data using the data tab. Okay, so the data seems to be populating correctly. The table info shows that the records are coming in at a rate of a few thousand records per second. Before we move to the next step, I want to highlight that I'm running this demo using Kinetica's free developer edition on my 2019 MacBook Pro. You can find the instructions for installing Dev Edition on Kinetica's website. One of the first tasks we want to perform is to calculate some summary statistics. This query calculates the number of observations, the length, duration, average speed, and bounds of each shipping track. The view is ordered from the longest to shortest track. You can think of a track as a time-ordered record of the lat and long coordinates of an object. Kinetica can use these timestamps and spatial coordinates, along with an ID variable, to create a native track object. The key feature of a track object is that Kinetica interpolates the path between two subsequent timestamps. This allows us to infer events like intersection with a geofence, which would have been missed otherwise. The next set of queries identifies the top 40 tracks by length from the summary view that we created just now, and selects one at random to display on the map below. The map is set to update periodically, so it'll continue to show us one amongst the 40 tracks as long as this view is available. Notice how we have combined different views to create an always-on pipeline of computations that keep themselves updated without additional inputs from our side. Each materialized view in this pipeline is updated either periodically or in response to a change in one of the inputs. The ability to cascade changes through a series of computations is a key capability when it comes to building an eventing system. We will use this in the next section to generate geofencing alerts. Let's go back to our workbook and set up our first alert. The area around New Orleans is experiencing bad weather, and the US Coast Guard is concerned about ships that are moving too fast in this region. You are tasked with setting up an alert via Slack that notifies the team when a ship moves more than 2 kilometers during a 5-minute period around this area. The Coast Guard has identified a zone around New Orleans that needs to be monitored. We will use Kinetica's st_track intersection function to determine if ships have intersected with this zone. But before we do that, we need to identify ships that are moving too fast. This materialized view calculates the distance traveled by each track over the last 5 minutes. The view is set to refresh whenever there is new data added to a table. So in effect, this computation refreshes about once every second or so as new data from the Kafka topic arrives into the ship_tracks table in Kinetica. We can see the IDs of ships that have traveled more than 2 kilometers over the last 5 minutes below. Now that we have the IDs, we can identify their tracks from the original shipping tracks data. This view is also set to refresh on change. Now we use the st_track intersects function to identify if any of the fast-moving tracks have intersected with the zone around New Orleans. This is another materialized view that is set to refresh on change. So we check for intersections with the zone whenever new fast-moving ships are identified. The next query simply selects all the fast-moving ships in the zone to display it on the map. Let's zoom in to see some of these tracks. The map is set to refresh every few seconds, so any new events will show up automatically. The final piece in our eventing pipeline is the alert itself. It is unrealistic to expect someone to sit and stare at the map until a new track shows up. Instead, we need an alert that is automatically sent out from Kinetica whenever there are fast-moving ships in the zone around New Orleans. For this demo, we will send these notifications out to a Slack channel. But these alerts can also be set up using a wide variety of data syncs. The Slack API requires a JSON object with a text field that contains the message that will be posted to Slack. Let's create a materialized view with just one field called text to capture that message, which in our case are the IDs of all the fast ships in the bad weather zone around New Orleans. Next, we need a data sync. A data sync is similar to a data source. It is an external data target, but instead of loading data from it, we stream data into it. We will configure this to stream messages to a Slack channel via a webhook. Now let's set up the stream. The stream listens for changes to the Slack alert_text view that we created just now and sends out an alert whenever there is a new text field, or in other words, whenever there is a new fast ship that is in the zone around New Orleans. Let's pull up Slack to see these events roll in. Note that it might take a bit of time before you see the alerts roll in. There, we see a few new tracks. Let's see if we can identify one of them on the map. We can click on a track to bring up the data associated with it. This track ID was the first in the new set of tracks that showed up on Slack just now. When we started this video, we talked about 3 criteria for an eventing system. The first was functional coverage, or in other words, the ability to discern an event using in-database functions. The second was the speed at scale. The third was the ability to cascade or chain computations together to create an always-on eventing system that can function without any additional human input. In this demo, we showed how Kinetica can be used to set up such an eventing system with ease. Now, there are 2 other alerts, one for dwelling and loitering and another for proximity with other tracks, but I'll leave those for you to try out on your own. All the code and instructions are available in the workbook. You can test this out using Kinetica's Developer Edition or Kinetica Cloud, both of which are totally free to use. The workbook for this demo is available in our examples repo on GitHub. I've pasted all the relevant links to get you started in the video description below. Thank you for watching.